Okay, this video is a quick overview of microglia. Microglia are the bodyguards in your brain, the macrophages, the immune system cells that surveil the brain under normal conditions, but when there's a problem like an infection or inflammation, tissue injury from traumatic brain injury, they respond to it. And the problem is there's too many false alarms where they're getting activated because of leaky gut and some other things too. So let me just show you what it's all about. This is useful to know, help to protect your brain. Okay, so here's the, well, first of all, let's start with a normal gut. In a normal gut, you've got your tight junctions, TJ for tight junction. These are the enterocytes lining the enteric tract. That's the gut. And the fiber is used by the good bacteria to make short-chain fatty acids, in particular 4-carbon butyrate. And just like a butanoic acid, the 4-carbon off of butane, the alkane with no carboxylic acid on it, so butyrate. The butyrate's used to make tight junctions, okay, and that's all good. The butyrate also gets into the blood and it goes to the brain, then you make the blood-brain barrier tight junctions as well. These are all things that cause leaky gut. Now here's the bad version. You don't have enough dietary fiber, you got something toxic that's causing leaky gut, you break down the tight junctions, bacterial endotoxins like LPS, there's also LTA, they can get across the gut layer and they can cause inflammation. That's what we care about now. If the big protein chunks get across from animal proteins, those can cause molecular mimicry, autoantibody cross-reactivity. The bottom line is those can cause autoimmune disease. We're not interested in that right now. Right now we're interested in LPS getting across and LTA getting across. All right? Now, so what happens with that? So what happens is the microglia in the brain, they're called microglia, the macrophages. In other locations, are often called dendritic cells. They look like a starfish. They've got PRR, pattern recognition receptors. So they will recognize LPS and LTA, and they will bind to it. And when they bind to it, they sense that there's an infection. So those are also called PAMPs, pathogen-associated molecular patterns. They can also be called MAMPs, microbial-associated molecular patterns. Because remember, it's all by Braille. They just feel something, and they sense whether it belongs there or not. And there's also DAMPs, damage-associated molecular patterns. If some tissue's been damaged, they'll recognize that it's not foreign, but it's still not supposed to be there, and then they clean it up. There's also something called CAMPs, cancer-associated molecular patterns. And the dendritic cells or the security guards are good at cleaning it up. Sometimes they're just overwhelmed, too much infection, too much tissue damage, so they have to run to the lymph node. And they go to the lymph node, they try to find other cells that will bind these problems and help them fix these problems. And then the immune systems pump out response cells to then fight the infection or clear away the debris or fight the cancer, whatever it might be. So this is just normal immune system stuff. Okay, the typical immune system cell is you're going to have a barrier, and this is all part of the innate immune system. There's going to be some type of barrier, your skin barrier, your gut barrier, lined with tight junctions, for example. There's an apical side or luminal side where it fights the outside world, whatever that might be, the stuff in your gut, the stuff outside your skin. And then there's a connective tissue basement membrane that attaches it to the rest of the organelle, the rest of the body. Okay, this is sort of like the usual way the immune system is set up. Okay, and so what ends up happening then is the innate immune system is mostly a barrier. It has a nonspecific reaction to things. And the infectious particles, whatever they are, or damaging particles come along. They'll breach the tight junctions. The dendritic cells fight, overwhelmed, run to the lymph node. They try to find matching immune cells that will fight whatever the particular infecting agent is. If it's bacteria, if it's some other form of parasite or something. Okay, and then they generate, the adaptive immune system can replicate and generate a specialized immune response, a more powerful immune response, but it's just slow to happen. The innate barrier of the innate immune system is always there. Adaptive immunity is slow to perk up, like for making antibodies or sending out T cells, okay? All right, and so where does this all come into play? Well, when you've got that defect in your gut wall, leaky gut, you'll get LPS particles, gram-negative bacteria, endotoxins, LTA, or the endotoxins from gram-positive bacteria, and they will get into the blood. And they will actually, number one, start predisposing the blood to clotting. And you'll get an amyloid type of clot where the secondary protein structure of fibrinogen, the blood clotting protein, changes from alpha helix like a cylinder, which doesn't stack well, to beta pleated sheets. They start stacking together. The bigger a molecule is in aqueous solution, the more likely it is to precipitate out. To precipitate out for a blood protein means to clot. and you start forming these clots. They're amyloid clots because they're not normal fibrinogen clots. These clots are more refractory to lysis, harder to redissolve. Okay, and they can go and plug up little capillaries in your brain, in your heart, and cause decreased cardiac function over time, decreased cognitive function over time. Very few people are aware of this. This is a really important thing to know about. It's another reason why you want to eat your dietary fiber and you want to avoid stuff that causes leaky gut. If you have an excessive amount of free iron, that can also become autocatalytic in your blood and ferrous redox cycle between Fe2 plus and Fe3 plus, and that can also lead to this type of clotting, this amyloid clotting in the blood. Okay, now here's a synapse in your brain. And the classic way most people learn about a brain synapse is the connection between two neurons. The blue is the presynaptic neuron, the purple is the postsynaptic neuron. Glutamate is the most common neurotransmitter in the brain, about 90% of cortical neurons. Glutamate goes across the synapse, binds to the postsynaptic receptors, exerts an effect on the postsynaptic neuron. This is an astrocyte. It sort of clears the glutamate from the synapse, then packages it, turns it into glutamine, sends it back as glutamine, so you don't want to be sending glutamate around outside the cells because it could start activating things. But anyways, that's called a tripartite synapse, of 3 parts. Presynaptic neuron, postsynaptic neuron, astrocyte. Okay, and the astrocytes are called the mama cells because they help the neurons to do their business. The neurons are the communicating cells that send messages. Okay, but there's a 4th cell here. Cell number 4 is the macrophage. And the macrophage is the cell that, the macrophage is called it has a specific name in the brain. It's called microglia. And it's sort of the bodyguard. It's the security guard. It makes sure everything is cool. The neurons are doing what they're supposed to. Nothing is trying to invade the brain. That's all copacetic, how it's supposed to be. All right, but if something bad happens, this microglia jumps into action. And in general, you want it to just take it easy and not do too much almost all of the time. All right. Okay, now here's the phases of microglia activation. All right, so you can have here normally, let me find what's a good spot for me down over here. Normally, here's a macrophage when they're resting. MO is called M0, N-O-G-H-T, naught. And so it's just not doing anything. It helps a little bit, surveys the brain, see if anything's going on, helps with neurogenesis, formation of new neurons, synaptogenesis, the formation of new synapses. Not too busy. That's the way you want it to be. A primed microglia means something happened. Imagine you have a bodyguard, guarding a building that's out in the middle of nowhere, okay? And so it's normally not doing much. It's just sitting around, playing solitaire, reading a book, okay? It's taking it easy. That's what you want. A primed microglia means that something happened. Maybe there was a break into the building, last week. So it's really kind of worried for the whole next, month or so. And so it's hyperreactive and it has a tendency to overreact, react too fast. That's when it's been partially activated for whatever the reason. Something's going on with it. All right, now what causes full activation? So a primed one means that it hyperreacts when it overdoes it, but it's not currently secreting any toxic chemicals. Okay, the M1 is the fully activated microglia. That's the one that's bad, okay? It's now, if it's fighting an infection, then it's supposed to be hyperreactive, okay? But if it's not fighting an infection, you don't want it to be in the M1 phase, okay? Because the M1 phase, what puts it in the M1 phase? What puts it into the M1 phase if you have excessive psychological stress. So excessive psychological stress causes microglial activation. It really is bad because people used to think, stress is no big deal. No, it is a big deal. And it'll cause microglia activation. If you have a hyperreactive brain, over time, this microglia is releasing toxic chemicals like activating its inos, inducible nitric oxide synthase. That's the one that stays on for too long and releases too much nitric oxide, leading to peroxynitrite, all kinds of damage. Tumor necrosis factor alpha, these inflammatory cytokines, and transcription factors, and they're going to lead to reactive oxidative stress and brain damage. You're going to be losing neurons. That's all bad. Okay, neuron apoptosis is happening. Okay, so don't get me wrong, sometimes it's useful. If you had traumatic brain injury, there's damaged brain tissue, it can clear it out of there. Okay, if there's an infection, it'll fight the infection. That's all good. But you can get activation of these things by just external things, LPS, lipopolysaccharide, LTA, those endotoxins caused by leaky gut. That's what I meant by leaky guts causing brain damage, okay? If you're on chronic corticosteroid medications for for asthma or something, taking those every day can be damaging to you because it'll start to process them in a different way and cause activation of microglia. We talked about atrazine and toxic chemical, volatile organic chemicals, smelly paint. You don't want to be smelling paint. Diesel fuel, smoke from tobacco and other types of cooking smokes, cooking fumes in the kitchen. You want to get them out of there, ventilate them with a hood or something. All right, well, anyways, these cause brain damage. M2s are the anti-inflammatory ones. They help restore things back to normal, restore homeostasis. They're neuroprotective. All right, here's another example. Some of the ways that these things can become toxic. So let's say you're right here and you've got a leaky gut, so the bacteria get into the body, or just the bacterial endotoxins, LPS and LTA. When you have leaky gut, you tend to have leaky blood-brain barrier. They get into the brain parenchyma. The pattern recognition receptors on the microglia bind to them, and it goes, uh-oh, that means there's an infection. And it'll just release tons of, its iNOS is turned on, inducible nitric oxide synthase. So you make tons of nitric oxide. This is a bad type of nitric oxide where you're making it for minutes or hours where you don't want to be making it. And it's just sort of sterilizing the area around the microglia. But unfortunately, there's collateral damage when it sterilizes the area. It destroys neurons. And there'll also be quite often superoxides in the vicinity or in the adjacent mitochondria. And then those will combine with the nitric oxide to make peroxynitrite. And these peroxynitrites are really bad. They destroy like lots of things, and they cause cells to die. So anyways, this is how leaky gut causes brain damage. So lack of dietary fiber over time is going to cause brain damage through this mechanism. This is one more of the mechanisms of neurodegeneration. And it happens on a local sort of micro scale, and it's microscopic, okay? So it doesn't show up on a brain MRI. Big stroke shows up on a brain MRI, but this happening in small amounts all over the place, it doesn't show up on a brain MRI. Okay, this is just showing, this is sort of like the apoptosis eat me signal of phosphatidylserine externalization, meaning that when a cell starts to not function well, it can't make ATP, then it can't maintain its flipase and floppase enzymes in its plasma membrane. And the phosphatidylserine, which normally should be on the inner leaflet of the plasma membrane, starts to flip into the outer leaflet. And the microglia senses that complement will bind with the complement immune system proteins. And the microglia will say, this neuron's toast, it can't make ATP anymore, time to destroy it and remove it. Okay, so there's a whole bunch of things that can do that. Chronic hypoxia, lack of oxygen, chronic hypoglycemia, lack of glucose, hypoperfusion, not enough blood going to the brain because you've overtreated your hypertension, for example. Atherosclerosis in the brain causing tissue hypoxia, so the oxygen can't get there. Synergistic effects with mitochondrial inhibitors. I've talked about that before in my lecture about the Pete Rogers theory of supply and demand, where you're not getting enough oxygen glucose delivery or ATP production because your mitochondria are inhibited. So these are all things that destroy brain cells, and then the microglia just comes in and cleans up the dead, half-dead apoptotic brain cell. This is how it works. And this is the main thing causing brain damage, is just these processes of apoptosis for all these reasons. And that's why when I look at most brain MRIs, all I see is a shrunken brain. I don't see an acute stroke typically, or a big bleed or anything, or a big tumor. I hardly ever see that. Okay, so anyways, this is just different ways that you can go to making peroxynitrite. This is the bad guy. This is called the NO-ONOO pathway of brain damage. Martin Pall is the big popularizer of the NO-ONOO pathway. I just sort of am putting, adding the details in, putting it into context with for neurodegeneration, destruction of brain cells. So here's peroxynitrite, the sort of evil villain destroyer, the monster. Destroys mitochondria, destroys the plasma membrane calcium ATPase, destroys the circuit, sarcoplasm, endoplasmic reticulum, calcium ATPase. And so this keeps going on. The cell's just toast, okay, and it dies. It goes into apoptosis, programmed cell death, which again is a gradual process. So anyways, I just wanted to summarize what microglia are all about as a mechanism of neurodegeneration. And the lesson to be learned there is, well, just avoid the stuff that causes that. Avoid atrazine. That's the herbicide that's really toxic. So only if you're going to eat any corn, it better be organic, okay? And then I try to only eat organic anyways. But, and the other things that are a traumatic brain injury, don't have your kid play a sport, or yourself where there's brain trauma, okay? And then all the things that cause hypoxia and all that, like we talked a lot about that before, all the mitochondria inhibitors. So that's what microglia in the brain are all about. So let them do their job and don't make them activated unnecessarily with all these bad habits, and you'll protect your brain.